So in this video, I want to talk about debugging because it's a subject we don't talk enough about. My name is Eskil Steenberg. I'm a C developer. I'm a member of the VG14 ISO C board, and I'm a game developer, and I think a lot about debugging. So in my opinion, debugging is the most important skill you can have as a programmer. And unfortunately, it's not something that we teach at school, or there are very few books or information about it. And I think it's a really, really critical skill. Because good code is not written, it's debugged. It's like the saying that good books are not written, they're rewritten. And I think that's very, very true. So when you debug, you need to really prioritize the things that are likely to fail and the things that are likely to be hard to debug. There's a bunch of things that may go wrong, but that are trivial and you're going to find them easily. And those things you shouldn't worry too much about. You should worry about the things that will really break things and the things that will be very, very hard to fix. You can't check for everything. And this is kind of a little bit of an attitude that some people have, that it's like you have to check everything. And if you check everything, that means you're not prioritizing. If you're not prioritizing, you're spending a bunch of time looking for things that aren't there, when you can actually spend time on the things that are important. So you got to prioritize. That's always important. So an example of that is, setting all warnings to errors. This is something that some people think is a really good practice, that you should just not accept any warnings whatsoever. And I think this is actually a very bad thing for non-obvious reasons. It's not really wrong to fix warnings. That's okay. The problem is that enough people turn this on by default, and that means that compiler writers become very, very wary about adding new warnings, because anytime they add a new warning, a bunch of builds are going to break, and a bunch of people are going to be mad, and a bunch of people are going to complain. And therefore, even though compiler writers want to warn for things, they don't feel like they can, because people turn this on and then they get mad. So be careful. And also, a lot of the really good warnings that compilers do give are not on by default for this very reason. So check your compiler and see what kind of warnings you can get. We all write different kinds of bugs. Everybody is different, and therefore we make different mistakes. We're not the same, and therefore it's kind of hard to prescribe of like, this is the right way to do things. I, for instance, is dyslexic. I'm going to make a whole bunch of mistakes that the vast majority of programmers never make. But then there's a bunch of things that I don't ever have a problem with that other people have a problem with. And so what I do is I configure my compiler to ignore a bunch of warnings that I don't care about. And then I take the warnings that I do care about and turn those into errors. And you can start building up a list like this. And anytime you see a warning that you really, really should address, put that on the list of things that should be an error. And over time, you'll build up a list, and you will get a much, much safer way of working. Debugging really starts when you write code. It's not just when something is going wrong. You really want to think about it throughout the whole process. And if you think about what debugging is you have a mental model of what's going on, right? You think the program does the right thing. The program doesn't do the right thing. So you're wrong about your code, right? You have a mental model of the code, but that mental model is flawed for some reason, right? And the goal of debugging is really to reconcile that. And this insight is really important, because a lot of people think that code is for computers to understand what we want. But a lot of it, when it comes to debugger, is us understanding our own code. The computer usually do, but we don't, right? And this is why readability is such an important thing. Why, having a language that is simple and readable and code that doesn't do any weird things is really, really key. And formatting matters, right? Everybody has different opinions about formatting, and you could argue some are better and some are worse. But what's actually really important is that you keep your formatting consistent. Because if you do, you'll learn how to read that faster. You think less about the syntax and more about what the code actually does. And that's why, although we will never agree on how formatting should be, it really is important. And so here's an example. Here is a switch with a bunch of stuff in it. This is from a project I've done. And here's how I indent this. So I indent all of the actual content. And this means that I very rarely forget a break in a case, because the breaks in the cases are very visible. And that's very important to me, right? And other people complain about, like, oh, you got to have like special things to avoid doing fall through. And I was like, what are they talking about? That problem never happened. And then I look at other people's codes and I go, oh, okay, I get it now. So trying to figure out ways to avoid those problems from the get-go is a really good idea. And that's kind of the thing, is like your compiler almost always understands your code and you don't. And that's why it really is about, like, the compiler is almost always right about your code, right? What it actually does. And you're almost always wrong about it. And that's kind of why your code should be read by you. And that's really important. And that's, why I think that anything that is clever about syntax or like saves you typing is almost always bad. And as someone who does a lot of programming, I get a lot of junior people to ask me, it's like, what is your tricks? And a lot of what they're looking for, I don't ever do. I don't do tricks, because tricks are hard to read. Tricks, makes you have to do an extra loop of thinking, and that's just generally bad. So here's some things that I think are just plain bad. I don't like macros. I don't like templates. I don't like metaprogramming. I don't like name overloading. I don't like operator overloading. I don't like invisible jumps like discards or destructors or anything like that. I want everything to be extremely clear. If something happens, I want to see it on the page, and really not have it jump somewhere or magically do something. And when it looks like elegant because it magically solves your problem, that means the bugs are also magical. And that's really what you don't want. So really beware of any useful tricks. The road to C++ is paved with useful. Everything in C++ is useful, but it's also hopeless to use. And when you look at languages and things like that, people tend to think, oh, that's a clever thing. That's a useful feature. And I almost always think, it's like, how could this be abused? What if I actually do it wrong? And most people don't do that. Even in language design, people don't think about this. People think, how does this functionality solve a problem? They don't think about how it causes a problem. So the goal here is to make your code as WYSIWYG as possible. What you see is what you get. There's no funky business. There's no magic. There's nothing hidden. What you see is what you get. That's really what you want if you want to have bug-free code. You should not be thinking about the syntax when you're programming. The syntax should just be automatic. When you see syntax of the language you're using, you just automatically know what it does and not have to think about it. If you have to parse through and be like, oh, that's a this thing, and that's a that thing, and this does that, and what does this do? Oh, it does that. Then you're doing the wrong thing. You should be thinking about the problem you're trying to solve, not what the syntax you're trying to express the problem in. So once I had a problem, I was working on a JavaScript system, and we wrote a value to a value and then read it as a different value, and we'd capitalize them, differently. And that basically meant that we wrote a value to one thing, and then we read out, default value of a new thing. And we spent hours looking for this thing. And in C, this would have never happened, because you would have a type def. You would have built the struct and put the thing in there. And people complain that, oh my God, why do I have to type this so many times? The computer can understand that I want one thing. And that's true. The computer can understand this, but it can't read your mind. And therefore, by declaring it once and then having it fail unless you've declared it, you're not spending those 5 hours looking for that problem. And that's why I always think that, like, saving a few seconds of typing is a really, really bad trade for getting a more complicated bug. Because typing is easy and debugging is hard. Typing is always easy. And, I stream a lot. You can check my stream. I'm one of the worst typists in the world, but I'm a great programmer. And those are two very different things. And actually, the faster you assume you're right about your code, when you are wrong, the longer it will take you to figure out why you're wrong. Like if you see a piece of code and you say, well, that's obviously right, and then you move on, if that code is then wrong, well, you're not going to go back and check because you've just said that it's right, right? And therefore, you really, really don't want to hide anything, right? That's super, super important. And this is like, there's a few lessons in this talk that I wish everybody could like internalize, and this is really key. Don't make the easiest stuff easier while making the hard stuff harder, right? If you save a little typing, but then get, some really obscure bug every once in a while, that's a bad trade. You traded something easy, typing, for something really, really hard, finding a bug. Or worse, the bug might not be found, right? So if you think about it, you can look at different bugs as like different severity. So you have compile error, right? If you make a syntax error, it won't compile. That's a super easy thing, right? It'll tell you, your code won't run, it'll be, it'll tell you what's wrong and you can fix it, right? You can have a tool error where maybe your compiler is okay with it, but you have some kind of linter or something like that that can tell you that this might not be okay. That again is really helpful, right? It's a little bit less sure because it might be correct, but it might not be correct, but it's still, reasonably easy to find. And then you get like runtime violations, you read or write to null or something like that. The program crashes, right? And then you have to figure out why. But at least the program crashes where it, went wrong. So you can backtrack, you can do kind of things. But then you get the harder stuff, which is it works, it just does the wrong thing, right? Now you may not even notice that it's a bug. If you notice that it's a bug, you have to go in and stop it where, try to find where it is and stop it. It doesn't stop by itself anymore. And then you have the really, really tricky bugs where you don't even know they exist, right? And they just, fly under the radar, that you don't notice them, but everything is like subtly wrong and maybe rarely break. And those are the absolutely worst bugs. So if you can move a bug from being a runtime violation to become a compile error, that's great, right? And you really have to think about this. Where do my bugs appear, and can I move them to the right area? And there are other things, if you have a super rare behavior, something that very rarely happens, or maybe you have a problem that's non-deterministic, so it's not repeatable. You can't reproduce something. That makes it harder, right? If something is on the heap, in my opinion, it's usually easier to fix than on the stack, because the stack, you're likely to overwrite other things that may cause weird things to happen, and much more likely that you're going to have a hard bug. So these are kind of general guidelines. If you can move things to be less bug prone and easier to fix, that's a general good rule. Yeah, you want to move your bugs to an easier category, right? So here's a discussion I've had an infinite amount of time, especially in the last couple of weeks, which is serial initialization. I think serial initialization is a really, really bad thing. And there's lots of people think that all languages is automatically zero initialize everything and then, everything would be better. And I think this is just a fundamental misunderstanding of what you want in a computing system. So one of the arguments is like, well, if we make zero a good default, then, if we miss adding something or doesn't set something, then it will work anyway, right? So we can look at this struct here. We have an array length and we have an array. Great, okay. So if this is 0 and this is null, then, those are reasonable values. We're likely to null check and, all is good, right? But that's an extremely superficial way of looking at it. If you look at this struct, what happens if I forget one and not the other, right? What happens if I say the array is 5 long, but the pointer is null? what happens then, right? Or what if the pointer is there and there's some data, but the array says 0, right? So you can't really say that this structure is safe just because, you set everything to null. Well, if you miss something, then it's partially broken. And since 0 is actually a reasonable value, it's much less likely that you'll find this bug. And I'm going to show you some examples of that. I prefer to set all my initialization in debug mode to CD. That's a Windows thing. You can pick any number you want. CD is a good number because it's very high. That means it's less likely to happen. It's less likely to be an address that you can recognize. I tend to set all bytes to CD. Some people set, a funny word like cafe babe or, some leet speak thing. I like having all bytes the same because you may not read that whole thing. You may just read with single bytes. And I happen to know that CD is 205. So any time I see a value that is 205, I know, this might be an uninitialized value, right? That makes it super easy to catch these things. So I'm going to show you an example, and this is a little bit more complex. And it actually sort of, if you don't follow this, then that's kind of the point, right? So here we have I've tried to make this simple, but, we have a data structure. Assume we have a bunch of other stuff. We have a text string in it. And I have a way to initialize this, right? And I should be setting this text string to null, right? That's what I should do. But I forgot. So this is the bug we're talking about. I made this, I failed to set this initialized, right? And then I have another function that prints the data, and it basically checks if this text thing is not null, then print it out, right? So, you could replace this with anything, do something with the data, basically, right? And now I have an example of where we're using this, right? So I have a function. It takes two strings, right? And then I start by allocating one of these structures. And in this case, I'm going to initialize everything to 0, which is a bad thing. And you'll see why it's bad. OK. And then I start using this. So I init my data, right? OK. So I think this sets this thing to null, but it doesn't, right? And then I say, hey, if this input happens to not be null, then set this value to null, like to the string A, right? And then, use it, print it, right? So what's going to happen here is if this thing is null, this is going to be null, and it's not going to print anything. Works great, right? If I did set this to CD, 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 it's going to say, aha, I'm going to not set anything because this is null. But then when I try to print it, I'm going to print address CD, 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 CD. And I'm going to have an instant crash, right? And then I'm going to find out, oh, my code is broken, right? But I didn't do that. I set this to 0. And that means that this code that is broken is going to work anyway, right? So I might write a test like this and be happy and say, oh, my code works fine. Look how good I was, right? But then we're looking at a more complex thing because we have two strings here. So what I want to do is, I initialize my thing. I clear all the stuff. I think I do that. I do this thing, and I print my thing, right? And then I want to reuse this memory. So now I clear it again. If B is null, then I set null, and then, here. So the problem here is if you run this code, it's going to work perfectly except for one time, which is if I do set A, so A is not null, then I'm actually going to overwrite the null in text. And then if B is null, I'm not going to overwrite that. So then when I print this, I'm actually going to print A, not B, which was what I expected. I expected to only write B if I did set B here, because it's supposed to be cleared here, right? And that means that out of all the combinations, there's 4 different combinations of this could be, a string, or it could be null, or this could be a string or a null. There's only one of those combinations that now actually, does the wrong thing. And when it does the wrong thing, it doesn't crash. It just prints the wrong string, right? So now you have a problem that is, you can write if this is your test, you're not going to find this problem, right? You're only going to find it in the rare occasion where these two are in this combination. And that means you've now made a bug that should be super simple to find, extremely hard to find, right? And that's why I say when you initialize memory, you want to initialize it with something that will break, not something that probably will be fine, right? Okay, let's move on. Set up your compiler to move problems, right? So as I said before, you can turn warnings into errors. People complain about C that like, oh, it's not type safe. No, if you implement a compiler, you have to allow for a bunch of things. But if you use a compiler, you don't have to allow for those things. You can just turn them off and say, if you warn me about doing type unsafe things, turn that into an error. Wow, now you have a type safe C. Don't have to make any change to the standard, right? And this is the second thing. Think about debug and release, right? So you want to release software in one state and you want to debug in a different state. Debugging code and releasing code are two completely different things. And how you think about what a language does should be different depending on if you're debugging and releasing. Okay, so if you're debugging, you want anything that goes wrong to fail really hard. And you want it to fail fast and you want it to stop. So you can't move on from that, right? In release, you kind of just want to move on, right? Because there's no real point in doing anything else. Like everybody's seen a Windows application crash that says like reading violation on X003FB whatever address, right? What's the point of that for the user? Like, what can the user do to rectify that? Nothing, right? It's too late, right? That's something that the developer should have done, right? And recently, Ginger Bill asked, like, what's the right behavior if you divide by 0? What should the language do, right? And in my opinion, it sort of completely depends, right? If you are in release mode, it doesn't matter because when you release the software, there shouldn't be any debug, shouldn't be any divide by error. So it kind of is it doesn't matter, right? But in debug mode, it matters a lot, right? You don't want it to break on the divide by 0. Preferably, you want it to break way before that. You want to break it when the compiler has said, you're about to create a number here that will be a divide by 0. And you want to stop at the moment that divisor is created and the compilers be like, oh, look here you're doing it. This is the bug here, right? And over here, that will cause a problem, right? So there's completely different point of view of what you want your system to do, right? And this is kind of key to a lot of how we design languages, right? A language cannot know what the right thing to do is, right? If you make a mistake, what then, right? Only the developer can say, if you get into a state, what the program should do, right? And some people like security people are like, oh, well, you did a buffer overrun. You should shut down the program instantly because this is dangerous. And it's like, well, that might be good, but what if the software runs in a pacemaker or another medical device or like maybe in a flight computer? Then just shutting down doesn't seem very responsible, right? And the compiler can't know these things. The only person who can know it is the developer. So the point is trying to make the developer aware of these issues before you ship, not try to ship bad things. Okay. It's extremely rare that you can actually do anything reasonably, when things go bad, because it's kind of too late, right? And this also minimizes the error handling, right? You don't want a bunch of runtime errors. You want a bunch of errors during development so you catch them so that when you actually deploy the code, there isn't that much that can go wrong, right? And this is why I think anything you build should have a debug mode. Having a debug mode is really, really powerful. And each module or piece of code you can do can have its own debug mode, right? Don't make it the debug mode of the compiler, because that's a different thing. If you have a bunch of things that, turn on to debug your thing, maybe you have a bug that only happens when your compiler is set to release mode, right? If you then tie all your debugging capability to the debug mode, You can't use any of your debug tools to find the error, right? So you want these things to be separate so you can turn them on and off independently of what the compiler does. You want to be able to debug and use your debug tools even if you're at the highest optimization level, right? Here's a very simple function that I show you what this can look like, right? So you have a function, it takes A and B, you have some kind of constraint like A can't be bigger than B, and then you create an if-defs with your debug mode, and then you print an error, and you can make it as verbose as you want and tell what's wrong. Now, nobody can call this function with the wrong parameters accidentally, because when you do, you get an error and it tells you what you did and things like that. This is really good practice. Make APIs that can't be used wrong, right? So let's talk about an example of that. I have a memory debugger, right? So this is my memory debugger. Let's see if I can... what it does, I'm going to find a different version of it. Hold on. So here we go. There's a clean version somewhere. I'll get it to you. It will be in the show notes if you want to look at this code. But what it basically does is it has a bunch of functions that are malloc, realloc, and free. And what we do is we do macros that replace them and add file and line, right? And then we have now a bunch of functions here where we can check the state of the memory. So let's check on the most broken piece of software you've ever seen, okay? So what I'm doing here is I'm using the Forge Memory Debugger. I am setting up a log, which is like I want to log what I'm doing, and then I do 2 allocations, right? And then I print some uninitialized memory, and then I ask how much I've consumed, and then I can print a list of all my memories with this. And then I'm going to do some bad things. I'm going to, do a buffer overrun. I'm going to do a buffer underrun. I'm going to free this pointer, and then I'm going to write to it after I free it. I'm going to free it again, just why not, right? I'm going to realloc, not the key pointer, but I'm just going to jump 1 byte in, and I'm going to reallocate that, so that's illegal. And then I'm going to allocate, an infinite amount of memory, and then I'm going to call bounds check, right? And then I'm going to do another thing here, which is I'm going to take a pointer from the stack and put that into my memory, and then I'm going to try to free the pointer to the stack, right? So now I've done like pretty much every mistake you can make, right? And then I can do, I can call stack reference and heap reference to check what I'm doing. I can stop logging, and I can close my file. So what do I get out of this, right? So, I get my memory content is CD, because I'm using an initialized memory. It's easy to find, right? I can read out my memory consumptions, which is super useful. I can get a memory report where all the lines of memory, right? And here is my actual code. So you can see I'm getting a whole bunch of errors here. I did an underrun and I did an overrun, and I see which line I allocated and where the memory comes from. So how does this work, right? This is magic. Well, what I do is I overallocate every allocation. I store where all the allocations have been made. I put magic numbers in the beginning and the end so that I know where, memory I'm not supposed to be able to write to. If I overwrite or underwrite, that will be, trashed, and I can look at those numbers and see if any of those numbers are overwritten, then I have an overwrite or an underwrite, right? And this is like something, I've implemented this in a couple of days. You can do it easily as well. You can make your own tools. And this kind of thing really, really helps you when debugging. Here's another, piece of code from the engine I'm currently working on. Again, I'm using file and line, which I get from a macro that, wraps this thing. And then in debug mode, I can, write whatever error. I also have a macro or replacement macro that will run something on error. So I can change this to exit, or I can change it to, a breakpoint or whatever I want, to make it easy to debug. But you really want to stop, because as soon as you make an error, you want to fix it right away. Okay, let's get to some debugging technique, okay? So you can think of a bug as, a murder investigation, except you're the murderer and the investigator. Okay, so what you really want to do is narrow down the bug, right? You want to divide and conquer. I see a lot of people who are not used to debugging. They just like try random stuff. That's not really a good way to find a hard bug. What you want to do is say, hey, can I guarantee that everything is good before this point or bad after this point? Can I narrow it down? That's really what you want to do. So a lot of times it's about information gathering. You want to find out as much about what's going on as possible. And number one, use a visual debugger, right? Visual Studio is awesome for debugging. It's terrible for a bunch of things, but when it comes to debugging, it's the best thing there is. There are other debuggers that are coming out, Rad Debugger and Whitebox and things like that. You should really be using a debugger. And I think actually when you think about what language to use, I would start by asking the question, what kind of debugger exists for the language? Okay. But you can also build your own little investigation kit, go CSI on that bug, right? So you might want to build, print functions that prints out data structures, like drawing functions that draw things on screen if you're making visual things, validation functions that validate your data structure, logging that writes out, everything that happens, right? And you might want to be able to load and save your data structure so that you can, if you have a data structure that causes bad things, you want to be able to save that data structure so you can load it back in and use it for testing, right? So the language knows a bunch of constraints, right? It says, this number can't be, divided by 0, or you can't read and write to that pointer. But most of your data is much, much more constricted than that, right? It can't just be like this string has to be null terminated. It's like this string is supposed to store a name, not, an address. And if you store an address, that might be a legal C string, but it's not the right thing, right? It's supposed to have the name of a person in it, not their home address. So you need to make there's a bunch of constraints that a compiler can never help you with. And you need to add those yourself, right? What I usually do is I write a validation function, a function that takes your data structure and you can put any number of tests inside of that function that makes sure your data is okay. And then you can just pepper those in your code everywhere, right? So here are a bunch of functions that deal with this data, and I can put a validation function before and after all of them. And that means that if I reach one of those, things that's invalid, it will tell me, like, if I get an error on this one, I know that, oh, one function did something bad because it was valid before one function and it was not valid after. Okay, I got to go debug this thing, right? And here's, for instance, a function. This is the file from Titan, which is my library for doing 2D geometry. And here is my mesh validation function. So it takes a mesh, it checks all kinds of things like, is the number of polygons in this more than the number of polygons allocated? And then I check, is it inverted? Does it point to vertices that don't exist, and all kinds of other tests. And this function might actually be kind of slow, and it's okay because you're debugging, just as long as it finds all the issues for you. On this, I have a whole bunch of drawing functions. So, I can draw things because this is a geometry library, so I need to be able to see what's going on. So I need a rich set of debugging functions for that. Let's do a demo. So I can show you my gaming engine that I'm currently working on. And here you can see all this debug information. You can see I can even go into an inspector. I can select an entity. I can see all the values inside of it. I can, go here. I can see the lines. I can select all of them. So now I get, various debug information about things. I have a debug mode for my UI. So the UI, I can see when I'm hovering over a button, whether I'm over the button or not. And all these things are super, super useful for debugging. And I'm actually going to show you, this is a screenshot of like what the thing looked like a day ago when I was debugging this shadow algorithm. So then I had all these lines being drawn, and I have lots and lots of tools for drawing in different colors and things like that so that I know what's going on. Okay, let's move on. Yeah, so if you think about it yourself as a murder investigator, it'd be really nice if you could repeat the murder any number of times, right? If you could tell the murderer, come back on Thursday and do it again at this time so that I can be there and see you do it, then, murders would be easy to solve. And therefore, it's really important to try to make your code deterministic so that you can repeat tests over and over and get the same results. And you may have to write some extra code for this to work. To make it repeatable, you want to make all the inputs maybe recordable. If you make a game where all the inputs are recordable and you can, replay everything, then you can really easily find that moment where things went off the rails, right? If you're making something multi-threaded, you're probably having a whole bunch of other problems that normally you won't have because multi-threading is hard. But just because you've added a whole bunch of new bugs doesn't mean that the old bugs go away. So make it possible to turn off multi-threading because multi-threading makes non-multi-threading bugs harder to find. So if you can turn off multi-threading, have a slow application, but a slow application where you can debug all the things that don't have to do with multi-threading, and then you can turn multi-threading on and debug all the multi-threading. That's a good idea, right? Let's say you have a bug like this. You have a loop, and it does something, and at some point this goes wrong, right? But it doesn't go wrong right away, right? X might be a very, very large number, so you want to actually run this through, and you would like to know when this does something wrong, what's the input of that, and why does it do it? So how do you stop the compiler from, how do you stop your debugger at the right moment just before it does something wrong, right? So one of the tricks I do is, oh, this is actually wrong. This should be this. If this value, I put an if statement here, and then I put plus equals 0. So this is just a no op. This operation doesn't do anything, but it allows me to put a breakpoint on it, right? And now this thing will run for 998 times, and then it will break, and then now I can put a bunch of breakpoints in, do something, and make it, step through whatever goes on the 999th iteration of this loop, right? And there's other versions of this. I always use the same. You could obviously use, multiply by 1 or divide by 1 or minus 0 or something like that. I don't do that. I always use the same one. Why am I doing that? Well, first of all, the compiler will be able to remove this. So if I forget something in my code, it will actually be able, it won't mean anything in release mode. But the other thing is really good. By using the same one, I can search for it. And that means I can search my source code for this string, and I know that I will never do this for any other reason than, making one of those dynamic bug points. And this is super neat because I can now move my C file between different computers, different compilers, and I don't have to have all the breakpoints in, in my project file. They just come with the source code, and I can enable and disable them whenever I need them. Okay. Here's another technique I use. Let's say this function gets called a whole bunch of times, and at a certain point it crashes. It works fine most, but at a certain point it crashes. So what I can do is I put a static int and a debug ID. Oh, sorry. And then I can increment that each time I run. And if it gets to a certain point, then I can check that. So maybe I have a bug down here that, something goes horribly wrong. And then I say, okay, what was the debug ID at the point where it broke? Oh, it was 42. I changed this to 42, and then I can run my program again, and then I can put a breakpoint on this, and now it says like, okay, I know it's going to break the 42nd time I run this function. Now I can see what's the state, what's the inputs, what are the states that make it crash, and I can step through it, right? Okay, so here's another trick that is kind of similar to this, right? So let's say I have a data structure, and I want to save this to a buffer, right? And then I have a function that, says, if I serialize this, this is how much memory I need, right? And then, I allocate that amount of memory, and then I have another function that actually writes to the buffer. And this function, stores out how much data it's written. So if everything works the way it should be, these two should give the same results. Let's say they don't. Okay, so how do I debug this, right? Well, one way of doing that is to make an infinite loop, right? So now in debug mode, I basically say, if these are not the same, which they should be, make an infinite loop where I keep asking for the size and keep asking, for it to fill it. Because now I can go through in my debugger and step through here and examine exactly what this does, and then back to this one, and back to this one, and I can go as many loops as I want in order to find out what's the difference between this function and this function. Why does this not give me the same result? I can go check all the values. And since I have an infinite loop, I don't have to restart my program. I can just go, 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 go until I find the bug, right? Another trick you can use if you use serialization and things like that is to, in debug mode, add magic numbers into your stream. And that means that, like, if you have a bunch of things that should go and you accidentally read or write a little bit too much or too little, all the data that comes after that is going to be out of sync, but that might not break things. It might do bad things for a while and then eventually break. And when it eventually breaks, you don't know where it broke. So it's really hard to backtrack. So then you can insert a magic number here and there. And then you basically say, now I've done this thing. There should be a magic number that can only be this value. And if it's not, I did something wrong, right? So you can put those magic numbers, between every operation. And obviously, the data stream will be longer and bigger. But that's OK because you're debugging, right? And that's a really good thing if you're making a file loader that can also save, or making a network protocol between two ends. You can have this, magic number insert debug ability. Here's another trick that I use a lot. Whenever I use indices, I try to use indices over pointers a lot of times. So if you have an array of data, maybe you've allocated 1,000 things. If you want to reference something in that, you can take a pointer off of that, or you can take an index, right? Means the same thing. But an advantage of using index is that an index is very easily human readable, whereas a pointer is much harder to know. An index that says 47 tells you that, oh, this is the 48th value in this array, whereas, a pointer is going to be something, and you have to do a bunch of math to figure out how far along in that array that pointer is. Another problem is that the pointer is going to be different every time you run the application, whereas the index, if it's deterministic, will be the same and will therefore be a lot easier to debug. And I argue that for indices, you should use unsigned ints. And I'm going to try to explain why. Here's a little example. So here we have a bunch of different indices, and we have a pointer, right? And I'm going to make a mistake here where I'm going to go -1 on all of these indices, right? So I'm off by 1. I've gone backwards, and I didn't mean to do that. And let's see what happens. So the examples we have here is a 64-bit integer that is signed, an unsigned 64-bit, signed 32-bit, or an unsigned 32-bit. Now I favor this last one, and I'll show you why. So here we're going to, take our pointer. We're going to print the address that this index gives us, right? So we're off by 1, right? Now, if you actually run this program, what you will get is this. Now, the pointer I chose is 0, 1, 2, 3, 4, A, B, B, C, just to get you a pointer that's easy to read, right? Because we want to see what happens to the pointer. And if you look at all of these, they're all the same. They've gone from an F here to an E, right, because -1, with one exception, which is the last one, which changed the 7 to an 8. And that's because what we've done is had an index that is actually max 32-bit int, FFFFF. And that means we're not off by 1 byte, we're off by 4 gigabytes, right? And if you're off by 1 byte, you're very likely to be in legal memory. You're probably going to be in the same page of memory, which is okay to write in. And therefore, when you access this, you're going to be able to read from it and you're going to be able to write to it. You're going to read over and write over something bad, so something bad is going to happen, but it's not going to crash. Whereas this one that reads, 4 gigabytes off in memory, that is very likely to crash, right? And that's why using unsigned integers, 32-bit integer on a 64-bit machine will give you a lot more crashes when you do it wrong. So that's really what you want. The sooner you get the crash, the easier you can fix it. All these other ones will hide the bug, are much more likely to hide the bug, right? Okay, so finally, let's talk about tests. I kind of don't believe too much in tests. Text coverage is one of the stupidest metrics ever, right? This is like what manager says. It's like, if you've written a test for every function, then your code is good. That's kind of stupid, right? Because if you think about it, it's not about if your function is tested or not, if it runs. It's like, what are all the combinations of it, right? A lot of times when you write a function, you're immediately using it. So you're already testing if it can run by just using it, right? There's no point in writing a separate test just to test the thing you're already testing by running it, right? You want to test things when it actually makes sense, right? So write tests when you need them. I'm going to show you this. This is for a project I'm working on right now called Marshall. And this takes a bunch of code and parses code and does magical things with it. And here is a test for that. And there's a lot of things going on here. Initialization and all kinds of things. And since it is parsing a bunch of code, this code can look very differently. So guess what? This is generated. This is 1,000 different tests that tries all manner of combinations and things like this. And that's because when you know you're working on something hard and you know you're not going to be able to test it just by using it, then you write a test. So be really selective about when you write tests. And a lot of times it's much, much more useful to spend your time writing code that can be helped in debugging your code than testing your code. Okay. Yeah, and once your code is running, you don't have to put a test on it. Like people put tests in their build system. Every time we run this code, we have to test it. Well, if you're not touching your code, it worked last time, it's going to work this time. Why waste cycles on doing the test? Why make your build process slower? It doesn't make any sense, right? And what you want to do is write tests for things that you don't control, right? If you have code that someone else wrote and you depend on it, then you might want to have a test on it. If that code changes and that's going to break your code, well, then it's worth having a test for it, right? And in my opinion, when you don't know what to do, when in doubt, always write more code. A lot of times you can get stuck on any debugging problem and you don't know what's going on. It's completely mystifying to you and you don't know what to do. A lot of people just stare at the code, and I think that is a bad thing. You can stare at the code for a little while, but once you find that you're not making any progress, start writing debug code. Start writing that code that prints out all the values, detects all the things, and even if it doesn't really help you now, at least you're doing something. And if you're writing that code now, you might find it useful later. So instead of just staring, write more code. That's my advice. So that's my talk. I want to thank everybody for watching, and you can find me online. I'm running a gaming studio, so please follow us and check out what we're making. We're making a custom engine for a really cool game, or a bunch of cool games, hopefully. You can follow me on Twitter and on Blue Sky, and you can also find us on Discord, where we talk a lot of programming. So have a nice day, and thank you for watching.